So today I'm going to talk about our journey that started from batch normalization to stochastic whitening batch normalization. And this stochastic whitening batch normalization, or what we call SWBN, is our proposed method that's accepted in CVPR and will be presented in 2 weeks as well. So maybe we like in this talk, we have more time to go over some of the background as well. So first, I'm going to talk about the internal covariate shift problem and some background. So these internal covariate shift problem and batch normalization and deep feature whitening, these are mainly the background I'm going to give you. And then finally, our proposed stochastic whitening batch normalization. First, I want to mention that we're going to investigate what's this internal covariate shift problem, or first, we have to know like if that one is a problem or not, and how is it related to batch normalization, and if batch normalization is alleviating this internal covariate shift, because most of us we think that yes, that's a problem, and the batch normalization, that's the main effect of batch normalization to reduce this ICS. And then I'm going to talk about deep feature whitening and how this feature whitening is related to batch normalization, and how that one is an extension of that batch normalization. And I'm mainly going to talk about two main approaches, the Eigen Decomposition and whitening loss, or something that's called regularization method. And finally, I'm going to talk about our method, stochastic whitening batch normalization. So regarding the internal covariate shift, so this one is actually the change in the distribution of the layer input. So we can think of the changing in the distribution of the features at each of the layers of the network. But this change may be caused by two main factors. One of them is that the change in the input mini batch distribution. And this one, because we're sampling from the whole batch, so although we are like uniformly sampling from the batch, this sampling may change that distribution. So each mini batch that we're getting, we may get a different distribution. The second cause is that any updates that we're doing on the parameters of the layers may change the distribution of the subsequent or the next layers. So these are main causes of internal covariate shift. But we already believed that there are some negative effects of ICS over our networks. But what I say that, okay, these are misbeliefs, because the recent papers are showing that ICS is not as problematic as we were thinking before. So some of these negative effects that we were thinking that is happening is that it causes exploding or vanishing gradients. It slows down the training process, and it negatively impacts the generalization. So in the next slides, I'm going to talk about some of these aspects. But what is batch normalization? Batch normalization is, has been arguably one of the most successful architectures in architectural innovations in deep learning. From my own experience, I can say most of the methods, the optimization methods, or most of the innovations that we have had in deep learning, they're valid in some special cases or some specific problems, and we cannot really generalize them to most of the problems. But batch normalization is something that maybe 90% of the time, when you apply to your networks, you will get better results. So it means both in terms of the generalization and the training time convergence. So that's why it's very popular, and almost everyone is using that. But the problem is that we don't have very good understanding of the batch normalization and like how what's the effect of this batch normalization over our training and generalization. So what we were thinking was that this batch normalization improves the training of our neural networks by stabilizing the distributions. Maybe that's the case, but we're also going to show that there is a recent paper that's showing that this ICS, or internal covariate shift is not that much correlated with batch normalization. So what is batch normalization? This is just a simple normalization layer that we can put before our activations, or we can also put it after our activations as well. And the way that is defined is that we have a feature vector, and for each of the dimensions of that feature vector, we're going to calculate the mean over the batch, and we're going to calculate the standard deviation. And we're going to standardize each dimensions independently. So I'm emphasizing we're doing that independently from the other dimensions of the batch. And then we're going to have this gamma and beta parameters that are affine transformation. These are mostly going to keep the distribution. They're going to transform that distribution such that we get the best loss. We can minimize that loss at the end. So it means that these two parameters are learnable, and they're dependent on the task loss. However, that mu and sigma, they're not learnable. They're mostly are estimated based on the statistics of the batch, of the mini batch. So some of the advantages of batch normalization are as follows. It is shown that it stabilizes the training process, but this stabilization is not because of stabilizing the distribution of the features. So it mainly happens because it yields a significantly more smooth optimization landscape. So this one is something that is shown in this paper that you can see here. Shibani et al., they showed in the paper, how does batch normalization help optimization? They show that the main effect that this batch normalization has is smoothing out the optimization landscape. As a result, because we have a smoother landscape, it reduces the probability of exploding and vanishing gradient. And but the other thing is the problem of generalization. We believe that, okay, batch normalization is improving our network generalization. But why is that the case? Maybe it's not completely understood what's happening, why it's improving the generalization. So some of the observations that myself had was that when we are increasing the mini batch size, this generalization decreases. So it means that this generalization maybe is the result of the noise, the gradient noise that we are having as a result of using a mini batch instead of using a full batch. So in other words, batch normalization is not that much effective if you use the full batch. So the last advantage of batch normalization is that it improves the training convergence rate. And this one is because it reduces the maximum eigenvalue of the Fisher information matrix. And by reducing this maximum, it gives us, it allows us to use larger learning rate, or it increases the effective learning rate of our optimization problem. So in these figures, you can see on the left side, we have the standard training curve, and that's the orange curve, and we also have the standard plus batch normalization. As you can see, batch normalization here improves the convergence.
Ehsan, I ask you a quick question regarding this, like the change in the eigenvalues. Does it really touch only the maximum, so the minimum remains the same, or it improve the condition number of the Fisher information?
Actually, it improves the conditioning of the Fisher information metrics, but I've not seen much work on the minimum one. So it's mainly there is a recent paper they're talking about by reducing the maximum eigenvalue. But that's a very good question.
Yeah, because you really, I mean, in terms of inverting the Fisher information, that gives you the variance, like the condition number max divided by mean matters.
Exactly. Yeah, I'm going to talk about that one as well. So how this conditioning is going to improve also like batch normalization is improving that conditioning, and whitening in the next topic, that whitening is going to improve that conditioning of the Fisher information metrics as well. Sure. So is there any other question? Okay, so on the right figure, so you can see that we have the training curve in the standard case that convergence is not happening much, but with even a smaller convergence learning rate, that's a 0.5, we're also getting very good training convergence. And this is because that Batch normalization is increasing that effective learning rate in our optimization problem. So now the question is that, is the effectiveness of batch normalization due to that internal covariance shift reduction? Or how are these two related? Because we were thinking that this batch normalization is alleviating the ICS effect. So in this paper, they're proposing an experiment, and by doing that experiment, is showing that no, that's not the effect. So what they do is that they add some noise to the batch to the output of the batch norm activation, batch normalization. Sorry, the activations that are the output of the batch norm. And with that method, that's something that's called noisy batch norm. They show that like by adding that noise, they're increasing that ICS. However, the convergence rate is not decreasing that much. So here you can see this orange curve is the standard one, and the blue one is the curve with batch norm. But after adding this this noise, the convergence rate is still better than the standard one. However, the ICS is much worse than the standard one. So it means that really increasing that ICS is not reducing our convergence rate. So here you can see on the right part, on the right figure, that these are the distributions of the activations on different layers. In the standard one, you can see that we almost have some stable distributions. When we are adding this batch norm, these distributions are more centered around 0. However, we are not seeing that much stabilization of this because we were expecting that these distributions will become more stable in comparison with, for example, the standard one. So, but that's not the case. So at least these distributions are very similar to each other in terms of their stability. But when we are adding this noisy batch norm, you can see that this distribution is changing a lot. However, although this distribution, the variation in this distribution is increased, we don't see that convergence rate problem. They also come up with some metrics, some measures for to quantify this internal covariate shift, and their metric is as follows. So they're changing these parameters of the network, and before and after that update over those parameters, they're going to see what is the effect of this one over the parameter over the loss surface of the next layer. So by comparing these two, they come up with an L2 difference norm. So it means that the larger this norm, it means that we're going to have increased internal covariance shift. As you can see on VGG, we don't see much difference between the ICS of the standard curve versus the batch norm one. So here the red curve belongs to the standard one, and the blue one belongs to the batch norm. So even at the end of training, you can see that the standard one actually is doing better in terms of the ICS. The same phenomenon, you can see that in terms of if we use the cosine angle as a similarity metric, we also don't see much difference between the ICS of a standard versus the batch norm one. However, they use another network that is deep linear network. And in this one, they're not using any non-linearity or activations. They're just using a linear activation. But they also do another thing. They also use a full batch instead of mini batch. And it's very surprising that the standard version, actually it has much lower ICS than the batch norm one. So probably this one means that maybe this ICS is correlated with the batch size as well. As here, like in terms of the cosine angle, you can also see that the standard one is almost the angle, the similarity is almost one. However, the batch norm is not doing that good. However, when you look at the convergence rate, you can see that a standard plus batch normalization is converging much faster. So in other words, when we are adding this batch normalization, this ICS even increases. However, we're not, still we're getting better convergence rate on the training curve. So then what's happening really? They're showing in this paper that batch normalization yields a significantly more smooth optimization landscape. And probably this is the secret behind using this batch normalization and how it's helping our optimization. And they're using multiple metrics to quantify the smoothness of this optimization landscape. For example, they're using this loss landscape, gradient predictiveness, and beta smoothness. And based on that, as you can see, these red curves belong to the standard, and these blue curves belong to the standard plus batch normalization.
So may I ask you, Ehsan, regarding another perhaps operation that does the smoothing? We know that like a skip connection in appearing in resonance also smooth, not it doesn't like correct the covariate shift somehow, but at least we know it smooths the loss landscape. I wonder what happens if you compare adding like a skip connection that only does the smoothing of the loss landscape compared to batch normalization that does somehow, it's controversial, that does both somehow, or still it's unknown, the argument is not clear. So would you compare these two and what are the advantage and disadvantage of these?
Yeah, actually I cannot comment on that. So we need to do more experiments on the comparisons, because one of the things that we can see, some of these methods that we're using, they have a lot of overlap, and in terms of the effect that they have on the network. For example, this batch normalization and Adam optimization. So for example, we see that when we're using this batch normalization, this Adam optimization is not that much effective, because this batch normalization
somehow already in the batch norm, right?
Yeah, yes, exactly. So it means that batch normalization is already improves that conditioning of our Fisher information metrics, and Adam is trying to use that information that is already reduced or maybe extracted by the batch normalization. So that's why most of these methods, based on my experience and also like literature review, they're very correlated with each other. So especially like I'm going to talk about, for example, second order optimization, and also how it's connected with whitening. And you can see that this batch normalization, second order optimization, they're like talking about almost the same thing from the different aspects. But I've not seen any research that they're comparing the effect of that skip connection, that, as you mentioned, it's also smooths out the optimization landscape, and as a result, it reduces the probability of vanishing gradient in our networks, and batch normalization. But that's a great research area to
Thank you.
Yeah, thanks for your question. So next, I'm going to talk about feature whitening. And so how is this feature whitening is correlated with batch normalization? So what we're really doing in batch normalization is that we have the covariance metrics, and we want to make the diagonal of the covariance matrix an identity. And this one is as a result of the standardization that we're doing. So it means that we're dividing each of those ones based by its standard deviation, and as a result, the covariance matrix is supposed to have an identity diagonal. But now the next question is that is this enough, or we can go further? We can we push the off-diagonal elements of this covariance matrix to zero? So it means that can we reduce or remove that correlation that we have between different elements of that covariance matrix? And this is something that's called decorrelating the covariance matrix. So this one actually is very advantageous, because people have shown that it increases the convergence rate. So what it means is that whitening the covariance matrix usually increases the convergence rate. And in this diagram, you can see like how it's really happening. It actually improves the conditioning of the feature covariance matrix. And by improving this conditioning, it will improve the conditioning of the Hessian matrix and feature information matrix for the whole networks. So this one actually is happening for each of the layers, and for the whole network, this is going to happen. And as a result of this better conditioning, we're going to have a faster training rate, or like it's going to improve our convergence rate as well. But how about generalization? We don't know. Actually, I'm going to talk about that one as well. So it means that what's the effect of whitening over generalization? And similar to batch normalization, it's not that much work done in that area, but that's also a good area to work on. In the next, I'm going to talk about two main approaches of whitening, deep feature whitening. The first one is based on Eigen Decomposition of the covariance matrix, and the second one is based on adding a type of loss or regularization term that belongs to the whitening. And by adding that term, we're trying to impose that kind of whitening over the features of the networks. So first, I want to talk about this Eigen Decomposition. And what's happening here is that that's very simple. We're going to have a whitening matrix or linear transformation matrix that's W. And by multiplying this W by X, we want to get a covariance matrix that is equal to an identity matrix. So it means that the covariance matrix of X is not identity, but we're trying to make it an identity matrix at the end. So the question is what are the methods to obtain this W or whitening matrix? The first one, actually, this Eigen Decomposition method, what it's doing is that it first Eigen decomposes the covariance matrix like this, and then people we can use like PCA, we can use ZCA or Stochastic decomposition, and each of these methods has like its own properties. For example, people have shown that using ZCA is better than PCA because it keeps it maintains the spatial correlation of our input data or our features. So that's mainly because we're taking our X where we have this transformation, and then we normalize our eigenvalues, and then we take the inverse of that transformation. That's why it's not affecting the spatial correlation of the original data. But the problem here is that these methods are really computationally very complex. So in terms of the computation complexity, they usually are of the cubic order of 3, and that's why we need some very efficient methods to calculate this, to find the whitening matrix. So in the literature, you can find many works in this area, but some of the works that I was really interested in, there's a great paper by Google, Natural Neural Networks, And I'm going to talk about that one in the next slides, but there are also other papers for other methods proposed. We have generalized whitened neural network, decorrelated batch normalization, and iterative normalization. And this iter norm is, I guess that's a state of the art. And in our paper, we're also comparing our results with iter norm results as well. So natural neural networks. What's the idea here? What they're doing is that they're saying that, okay, so we want to improve the conditioning of this Fisher information matrix. Can we make it as an identity matrix? And if we can make it an identity matrix, this stochastic gradient descent and natural gradient descent are going to be equal. Because in natural gradient descent, we use the inverse of this Fisher information matrix. And if that's identity, the inverse is going to be identity, and these two are going to be the same, equivalent. In their paper, they're showing that they're not completely whitening it, but with some assumptions, they make it like very close to an identity matrix. Actually, they're also doing it blockwise. So the architecture of their method, their network is as follows. So we have this input X, we have this whitening matrix U0, whose output should have identity covariance metrics, as you can see here. And then we're also having some fully connected parameters that these parameters are being learned based on the task loss. So this one actually is learned based on the statistics of the mini batch, but this one is learning based on the task loss. And as you can see here, by multiplying by UI and then VI, and they're also using a function F, a nonlinearity function, that is our activation. So this actually equation shows the relationship between the features between subsequent layers. So, but how they're obtaining this U, that's the whitening matrix. First, they estimate the covariance matrix, and this covariance matrix is estimated based on the statistics of the mini batch. And then they apply a ZCA or PCA or any method. Here, they're in this paper, they're using ZCA for their to estimate the whitening metrics. Then they came up with a method that's called projected natural gradient descent algorithm, or PROG. And the main idea is that, as I mentioned before, that's how we're comparing the SGD with natural gradient descent. So in this space of theta, let's suppose that we want to estimate that natural gradient descent in this space, in this optimization space. So what we can do, we can take this one with this prong, with this projection to a space that is whitened space. And if we can take it to that space, we can do a stochastic gradient descent steps, as many steps as we want. And whenever we want, we can go back to the original space. And the natural gradient descent in this space is going to be equal to the stochastic gradient descent in this space, in the whitened space. So these are
a bit regarding the matrix that you're multiplying to make like the whitening of the features. Well, in the batch normalization, well, we have a single univariate scales, right? Gamma, and I don't know, you should beta, I think, in your formula. Right now, you're like making a matrix multiplication that has much more parameters, but has the advantage of making them independent, because with any scale and a shift, you cannot make the features independent. It's like scale invariant and shift invariant. But your increasing number of parameters and also evaluation of Hessian becomes the second problem, because, well, with these many parameters that we have in neural networks, it's difficult to estimate the Hessian appropriately. Could you please a bit elaborate on how this method could be used in real training of neural networks that has these many parameters?
Sure. That's actually the whole point, that like unlike the second order optimization method, that we need to calculate that Fisher information matrix, or we need to calculate the Hessian of our loss. Here we don't need to do that. So we are bypassing that problem. So I will show you what's this projection that I was talking about here. So what's this like inverse projection and projection? So what we're doing here, we're taking that we're finding the mapping between the non-natural gradient descent or non-whitened space and also whitened space. And
But,
after this mapping, we don't need to
like weight matrix that you are like adding to it to be like sort of a linear layer you're adding, and you hope that it will correct the whitening.
Sure. So actually, that linear layer is maybe that's something that's required by this approach. But in general, we don't need to apply that kind of linear layer. I'm going to talk about that one in regularization methods. And in those ones, you will see that we don't need that those linear layers. So, and adding that linear layer is not really, I can say it's not really making the problem, make the optimization overfit. Because we also have another constraint, and that constraint comes from the identity and the covariance matrix to be an identity matrix. So that's why adding those parameters is not reducing the generalization of our problem. If that's like what you asked, right?
Yeah, maybe it's a question at the end that how you will check that it becomes the identity, because well, checking that it's identity requires evaluation of Hessian anyway.
Not Hessian. So we're
expectation of Hessian, right? The covariance of U with. So okay. So maybe I get back to this at the end of it.
Definitely, yeah. So we note that we are working in two spaces. So one of them is the covariance of the features. So we're working on the feature space, and the other one is the parameter space. So our feature information is matrix is mostly working in the parameter space, and loss and the loss with respect to our parameters. But our covariance matrix is based on the feature space.
Of the parameters, it's the covariance matrix of the features.
Exactly. Yes. That's right.
That they are closely related. So good. But this
very
evaluate. The other one is difficult to evaluate. So to try
totally. Yeah. So one of the one of the things that I really like about this paper is that they come up with the whole framework about how are all these concepts are related to each other. And so that's what, like, I really encourage you to read this paper because you will see the correlation, the connection that we have between the second order optimization, whitening, and covariance metrics, Hessian, and like feature information metrics. So this is kind of a very good paper.
Thank you.
So sure. If I want to talk about the algorithm, so different steps of the algorithms here, their algorithm here. So let's suppose that we have initialized this UI. This is the whitening metrics here, and we have also initialized this VI, the learnable parameters. We're going to have this WI. This WI is happening in the same space as this theta. So now what this one actually is doing, it's kind of inverse that's an inverse projection from this whitened space to the W space, from this whitened to the W. And after estimating this W, we're going to estimate the mu and sigma of our based on the mini batch statistics, because now we have this W, and then we can calculate this H, and then we can come up with the mini batch statistics, mean and covariance of that. And using that covariance, we can easily estimate the this whitening matrix by Eigen Decomposition over the covariance matrix. And then here we're going to project it back to the whitened space. So this this projection that you see here, this is actually this projection that goes like from this canonical parameter space to the whitened space. Then after we transform actually in the whitened space, then we can do SGD iteration as many times as we want. But there is one trick that they're using here, because this process is computationally complex. So this Eigen decomposition, as I mentioned, is the computationally complex. The trick is that they're not doing it over each iteration of the training, and they're just doing it over some specific intervals. So at some intervals, they extract this whitening matrices, and then they're going to fix that one over the rest of that interval. So I'm not saying like what's like, definitely there are some errors that are going to happen because of this one, because it's not like fixing that whitening matrix over multiple iterations. It will introduce some error to our optimization problem. However, maybe we don't have any other choice, and we have to reduce that computational complexity. This is one of the ways that they did that. So here you can see the results of applying that whitening and this projected natural gradient descent algorithm. So this one is before this whitening, and this one is the Fisher information matrix that is obtained after applying the whitening of the feature vectors. As you can see, this one is more diagonal, or at least we can say that's a block diagonal metrics, like similar to KFAC, an algorithm proposed by Martens and Roger Gross in University of Toronto, and they're very similar to each other in terms of the Fisher information metrics that they're giving. But that's KFAC, for example, is a second order optimization, but this one is the whitening method. So I'm trying to say how these ones are very connected to each other. So this one, back to your question about conditioning, you can also see how the conditioning is improved. So this one is the relative conditioning relative to the initial conditioning value, and this conditioning value is largely decreased in prong. So this one is the prong method, and this one is RMS prob, and we also have SGD. So it means that whitening that Fisher information matrix also is going to reduce that Fisher the conditioning. But now the question is that we have improved the conditioning. We have whitened our Fisher information matrix. Now the question is that what's the effect of this whitening over our training curve and also the test curve? And here, this A and B, they've applied their method on CFAR10 data set, and also C and D belong to ImageNet. Here you can see the training curve comparison between a prong. This red curve is a prong, and this one is the green one is Basham-Lays, and the SGD is this. So it's very interesting that, as you can see, prong is largely improves the convergence rate of at the training time. However, at the end, it gives like larger training error than Batch normalization. On the test side, that is, these curves are more important for us. You can see that also the test convergence is much better than batch normalization, and we're also getting lower test error than batch normalization and SGD as well. So it means that it improves the generalization as well as the convergence rate. On ImageNet, maybe this difference is not that much visible, as they both prong and batch normalization, they converge to a similar validation error. However, prong is converging much faster again. When we are comparing their wall clock time, however, we have to be careful because prong is now computationally more complex, and then it takes more time in wall clock time than the batch normalized method. So next, I'm going to talk about the second approach that we have. And this one is very straightforward, very simple. And we don't need to add any whitening layer or something. And we just we're defining some regularization term based on the whitening loss. So it means that we are defining some whitening loss, we're adding that to the task loss, and we apply to our networks. And we don't need to change anything in our network. No whitening, extra whitening parameters or so. And there are some methods based on this one, and you can see reducing overfitting in deep networks by decorrelated representation. I'm going to talk about this one, but there are also other methods and more recent papers as well. So the first one that is called Decov regularizer, it defines the whitening or decorrelation loss with this equation. So what's this equation? So this one is saying that we want to calculate the Frobenius norm, the difference between the Frobenius norm of the covariance matrix and its diagonal, the Frobenius norm of its diagonal. With minimizing this one, we actually try to remove those the elements of the covariance matrix that are off diagonal. So as a result, we're going to come up with a whitened covariance matrix. And the covariance matrix here actually is calculated over the mini-batch, so based on the mini-batch statistics. As I mentioned, so the great thing about this method is that it doesn't need any requirement to add a whitening layer and can be applied to a single layer or multiple layers. So some of the results, experimental results about using this type of whitening loss, they're comparing their method with dropout because dropout is also a method that's for reducing that the correlation between different feature dimensions. And here you can see that when we just use dropout, we get the training accuracy of 99. But with Decov, we're getting the training accuracy of 88. So dropout is doing better in terms of the training accuracy. In terms of the test accuracy, actually the Decov is doing better because this is like 79 versus 77. But if you find the gap between that train and test accuracy that we have, we see that really this Decov is giving better generalization because that gap for just using dropout is like 21%, and for Decov is 9%. And if you use both of them together, we're going to have even less error, less gap. It means that it's going to give better generalization. They also have similar experiments on ImageNet using top 1 accuracy and top 5 accuracy. You can also see the results. They're very similar to the CFAR10 results. But something that I should add is that here, by just using Decov, you see that the generalization gap that we have is 6%, almost 6%, and it's very similar to just combining this Decov with dropout. And you can see that even what it means is that Decov is generally giving very good generalization as a whitening method with very simple like decorrelation loss. We can get very good generalization. But some of the limitations of these methods are as follows. So for example, for Eigen Decomposition, even you remember that natural neural network, they need to do Eigen Decomposition. And for that one, that's of order of cubic. So if we do that on like each iteration from scratch, that's going to be a huge computational complexity for us. Now we have to think about that. Is it worth having that much complexity versus batch normalization? So the second thing is that at each step, they compute this ZCA whitening from scratch. So it means that no information about that whitening matrix is carried over different steps of the optimization, like training. These are some of the issues that we have kind of reduced, or we can say we've removed in our method. And also there is no need to fully whiten the activations at each step, as it may reduce the network generalization. So this paper, the recent papers, it talks about the effect of whitening on generalization. So the paper is called Whitening and Second Order Optimization. Both make information in the data set unusable during training, and can reduce or prevent generalization. In short, they're claiming that whitening a second order optimization, they're reduced to generalization. However, if we use that whitening along with regularization technique, so they show that actually the generalization improves a lot. So one of the things is that if we come up with an algorithm, whitening algorithm, that we claim that this is fully whitening the activations, probably it's going to reduce our generalization. But if we partially whiten it, as we are doing it in our method, so we're both keeping the information required for network generalization, and also we're reducing the computational complexity. In the regularization approach, the main limitation is that now we have a regularizer and we also have the task loss. Now, how to combine these two? So we also need extra hyperparameters to combine these two losses with each other. And now the other thing is that if you want to whiten all the layers of the network, now the other question is that how are we going to combine all these losses together? So these are some questions that really means that we need to have extra hyperparameters. We have to do a lot of hyperparameter optimization to minimize this one. Next, I'm going to talk about our proposed method, stochastic whitening Batch normalization. So this one is actually mainly worked in LG Toronto AI Lab in collaboration with LG America R&D Lab. The main idea here is that we're also defining some whitening loss, or maybe what we call it like whitening criterion. And this whitening criterion shows how the covariance matrix is close to the identity matrix. So if we can bring that covariance matrix closer to that identity matrix, it means that it's whitened. So what we're doing, we're first defining such a criterion, and then by minimizing that one, with this equation, with respect to W, we can obtain the whitening matrix W star. So what we are doing, we're defining two whitening criteria, one of them based on KL divergence, the other one based on Frobenius norm. And so the details of this one is, you can find it in our paper. I'm not going into details. But this is the general framework of our algorithm. So what's happening in the forward phase, we first batch normalize the data. And this batch normalization is not a necessary step. However, we saw in our observation, in our experiments, that it makes our optimization more stable. So this we're applying this batch normalization here. But after batch normalization, we are applying this whitening matrix. But now the question is how to estimate this whitening matrix. What we're doing, we're updating W by SGD, where gradient is approximated by the equations that we have obtained analytically. So what it means is that we're thinking that yes, we have whitening loss, and but we're extracting this W by SGD over that whitening landscape or whitening loss surface. And we're obtaining those gradients not by backpropagation, but analytically. And we're showing that this one actually is more stable when we're calculating those ones analytically. In one of the cases, we noticed that, I guess it's in the KL version, we noticed that the backpropagation needs the inverse of the covariance matrix. And if that's the case, it's not easy. It's going to, our backpropagation is going to be unstable as well. But then what we did is that we used relative gradient. And so for more information, you can find it in the paper, how we are using that relative gradient instead of the actual gradient in this context. So After we have this gradient, we can use any optimization algorithm that we have. We can use SGD plus momentum, we can use atom or anything else to obtain this W. But the other thing is that at each iteration step, we are not fully whiten it. So the fully whitening means that we apply many iterations over this W to optimize it, to optimize our whitening loss. But we're not doing that. We're just like applying one iteration and we're continuing. After we have this, what I call semi-whitened matrix at each iteration, we apply W on batch normalized data. And then in the backward phase, we estimate this gamma and beta using by backpropagating the task loss, and these can be easily estimated. So what it means is that this information is estimated based on in the forward phase, based on the mini batch statistics, and this one based on the task loss in the backward phase. We're comparing. So this one actually is our detailed algorithm. So I'm not going into different steps of that, but feel free to check our paper for the full description of the algorithm. However, in terms of the complexity, computational complexity, when we're comparing our SWBN with ITER norm, you can also see that both of them are of cubic order as well. However, our algorithm is 5 times faster because ITER norm is using the Newton's method, and they're optimizing. They need at least 5 iterations to get good results and like reach good generalization and convergence rate. However, we show that like just with simple SGD, we can get to that point. In terms of the memory complexity, we also see that we need 5 times less memory for our method. These figures show the effect of whitening in SWBN. As we were expecting, batch normalization is not really whitening. After 150 epochs, we are not expecting batch normalization to whiten our covariance metrics. But SWBN, as you can see, the SWBN, both KL and FRO, like Frobenius, they both can whiten the covariance metric.
Yeah, Ehsan, I wonder if we can speed up because we already reached to the limit.
Oh, sure. So in terms of training time comparison, you can also see that we are doing much better than this ITER norm, as especially, for example, for ImageNet dataset, we show that for ResNet V2 101, the training epoch time that we need is 38 minutes versus 184 minutes of ITER norm. In terms of test accuracies, you can also see on both on CFAR 10 and CFAR 100 datasets, you can see that the SWBN KL is doing better than ITER norm, DBN, and also the baseline batch normalization. Also for CFAR 100, we have improved the test results as well. So last but not least, we have also applied our this SWBN to the few shot classification. So previous results that I showed, they are for many shot classification problem, but this one we're also testing the results on the few shot classification. We have chosen some famous methods for few shot classification, such as matching network, MN, and prototypical network and cross-attention network. And on these two dataset, mini ImageNet and CFAR few shot, we also show that this SWBN is improving over batch normalization and ITER norm as well. So my last slide. So to compare our SWBN versus Eigen Decomposition method, we're showing that both approaches need to learn a whitening matrix. However, SWBN learns a whitening matrix without expensive matrix decomposition or matrix inversion operations. This is mainly due to the limited number of required optimization iterations, that probably because of using SGD with momentum or atom. So unlike full whitening techniques, SWBN's stochastic nature yields better generalization properties due to its regularization effect. And when we're comparing this SWBN with regularization-based, other like previous regularization-based whitening methods, we can see that both approaches minimize a whitening objective function using SGD optimizer. However, in our method, we are we're estimating those gradients analytically. We're extracting those ones analytically and use it in our SGD. And unlike these regularization-based methods, SWBN needs to learn a whitening matrix. So this is the maybe the one of the problems that we may have. So because we need more parameters, so it will increase the model size. So both approaches whiten the features gradually during the course of training, and SWBN doesn't need any extra hyperparameter to merge the regularizer with the task loss. So that's it. Thanks for your attention. For further, for detailed description of the algorithm, please check our archive paper, and the paper is going to be presented in CVPR 2021 as well. Thanks a lot.